we present a deep learning-based method named DeProCams for simultaneous relighting, compensation and shape reconstruction for projector camera systems. Projectors and cameras evolved greatly in the past decade with better image quality, resolution, and become smaller and cheaper. They can be combined and applied to many applications, such as presentation, spatial augmented reality, structured light, and adversarial attacks. In this paper, we focus on three main spatial augmented reality tasks: relighting, projector compensation, and shape reconstruction, and here are some previous work. Next, I'll briefly talk about the three tasks. First, relighting. As shown in the figure, we project the input images to the scene, and capture them using the camera, and the results are shown on the top right. The goal of relighting is to approximate this physical project and capture process with a model, such that it can simulate realistic new projection effects. In this paper, we use a deep neural network to capture this process, and I will discuss the advantages later. Second, projector compensation. Given a projector input image, if we directly project it to a non-planar and textured surface, the camera captured, or the viewer perceived effect may be geometrically and photometrically distorted. To address this issue, we can compensate the projector input image, such that when projected to the surface, it can cancel the distortions. Projector compensation can be solved using the inverse of the relighting model. Finally, in projector camera systems, structured light is usually applied to shape reconstruction. It starts with projecting and capturing a series of handcrafted patterns, then the object shape can be reconstructed by finding the pixel mappings between the projected and captured patterns. Clearly, the three tasks share a similar pipeline of finding projected and captured patterns, but traditionally they are addressed separately. To the best of our knowledge, there is no unified method to address them jointly. Because some methods require additional optical devices and radiometric calibration for relighting, and other methods may need additional structured light patterns for shape reconstruction. Moreover, there is no end-to-end trainable solutions, therefore we address these issues using a deep learning-based method. Finally, we propose a benchmark for relighting and shape reconstruction, and future work can compare with us without actual projection or capturing. Our setup is shown in the bottom left and consists of a projector and a camera. The goal is to approximate the projector camera image mappings, using a model pi and collected image pairs IP and IC. We propose to approximate pi using a deep learning-based model, named DeProCams, and we explicitly disentangle the geometry and photometry using two submodules, named depth to attribute and shading net, for rough shadings and photorealistic renderings, respectively. Our DeProCams starts with projecting and capturing a set of sampling images. Given a camera-captured scene image S, a projector input image IP, and intrinsics and extrinsics KC, KP, RT, DeProCams aims to infer the camera-captured projection IC. Firstly, in depth to attribute module, we have a learnable depth map, DC, with which we can estimate intermediate shading attributes, such as normal map N, light ray direction L, view direction V, reflection direction R, warping grid omega, and projector direct light mask M. Then, we warp the projector input image IP to the camera view using warping grid omega, and mask it with projector direct light mask. Afterwards, we compute rough direct light shadings, such as rough ambient S, rough diffuse and specular using the intermediate shading attributes. The next module is shading net for photorealistic rendering. Shading net consists of three subnets: 1, a surface skip branch SK1 with 3 convolutional layers, shown as blue blocks in the top, to pass rough ambient S to the output layer; 2, an encoder-like rough shading branch, shown as green blocks, that uses 4 convolutional layers, conv1 or to conv4R, to downsample and extract rich features of the rough shadings; and 3, an encoder-decoder backbone subnet, shown as red blocks, to capture rich direct and indirect light interactions. The backbone network consists of an encoder, conv1 to conv4, and a decoder, conv5, tconv1, tconv2, and conv6. The 4 vertical black skip connections between the rough shading branch and the backbone indicate that rough shading branch feature maps are added to the backbone ones. Moreover, the two black horizontal skip connections under the backbone network add low-level feature maps, conv1 and conv2, to the first half of the high-level feature maps, conv5 and tconv1. Meanwhile, the two low-level feature maps of the rough shading branch, conv1R and conv2R, are transformed by two skip convolutional layers sk2 and sk3, and then added to the second half of conv5 and tconv1. The two types of skip connections allow ShadingNet to carry low-level visual details to deeper layers, and to better learn complex interactions between the direct light and the scene geometry in the feature space. Finally, ShadingNet infers a camera-captured projection IC hat. With many training image pairs like IP and IC, we can train DeProCams by computing the image reconstruction loss between the model-inferred camera-captured projection IC hat and the ground truth real camera-captured projection IC. This loss is then back-propagated to update ShadingNet weights and the depth map. Note that the depth map is optimized during this training process without knowing its ground truth, because it is constrained by the intermediate shading attributes and the inferred image IC hat. Once DeProCams is trained, we can apply it to three spatial augmented reality tasks, such as relighting, projector compensation, and shape reconstruction. Firstly, relighting is simply a forward pass of DeProCams. In particular, given a novel projector input image IP depth to attribute warps it to the camera view and computes rough shading attributes. Then, ShadingNet aggregates the rough shadings and further infers photorealistic rendering. For projector compensation, given a desired camera-captured effect, IC prime, we first input the uncompensated image IP star to DeProCams, and DeProCams infers a camera-captured projection IC hat. Then, we compute the loss between the desired effect and the current inferred effect. Afterwards, this loss is back-propagated to update the projector input image, until DeProCams inferred image IC hat is close to the desired effect IC prime. Depth map is inherently learned by DeProCams, and with the intrinsics and extrinsics, we can compute the point cloud and normal map. Next, we show some experimental results of relighting, compensation, and shape reconstruction. Firstly, as shown on the left, we have a projector input video, and the corresponding camera-captured relit result is on the right. Note that this relit result is inferred by our DeProCams, and clearly, it looks realistic, and has a good quality. Here we show another relit example. We show a projector compensation comparison between the proposed DeProCams, a pixel-wise method TPS plus SL, and a deep learning-based method ComponNet++. In the first row, we show the projection surface, the uncompensated result, and the desired effects. In the bottom row, we have real camera-captured compensation from TPS plus SL, ComponNet++, and our DeProCams. Clearly, our DeProCams shows better compensation quality, especially in the white regions of the camouflage surface. We also show a comparison on video compensation. Finally, we show an example of DeProCams' reconstructed point cloud. For the benefit of the society, the source code, training and evaluation benchmark dataset, and experimental results are publicly available on GitHub. Thanks for watching.